Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogashri Pradhan, and with me here today, I have Hamed Darabi, who is the CTO of QRI. Today, we're going to talk about paper SPE 200,000, which is an easy number to think about. The paper title and the description is in the description box below for our viewers and listeners in Apple Podcasts and YouTube. I'm going to introduce Hamed for a little bit before we start peppering him with questions. Dr. Hamed Drab is a Chief Technology Officer at QRI. He has expertise in AI, machine learning, and computational fluid dynamics. He is focused on digital transformation in the energy space. He leads the development, deployment, and commercialization of Speedwise Galaxy, a suite of AI-driven cloud-native products in collaboration with key partners such as AWS and Emerson. Dr. Darabi received his PhD in engineering from the University of Texas, Hookham, where he has extensively studied numerical and mathematical modeling. He has over 12 years of industry experience and has authored or co-authored more than 30 technical papers. That's awesome. Welcome to the podcast, Hamed.
Yeah, no, thank you, Yogashri. I mean, thanks for having me here. It's a pleasure talking to you.
Awesome. Well, before I start peppering you with questions about the paper, I wanted to ask you, what are some of the latest technological advancements that QRI is currently investing in?
Well, I should say, I mean, technology advancement in QRI really is never ending. I mean, from day one, the company was established as a value creation enterprise and with a big emphasis on innovation and technology development. And our Speedwise Galaxy suite has arguably the most comprehensive set of AI-based technologies in the industry for upstream decision making. Maybe one thing that changed over the past couple of years is in the past, we've been using these technologies primarily for our internal use to help some exclusive customers to improve their production, reserves, capital efficiency. And now actually we have partnered with some of the best companies out there, such as AWS and Emerson, to commercialize this Speedwise. And today, 4 of these products actually offered in the market as a software as a service or SaaS in a cloud native format. On the R&D side, I think 2 projects that I'm personally very excited about are one is the subsurface network modeling using physics-informed graph neural networks. And as you know, probably graph neural networks are one of the hottest topics in the machine learning community, and they're also extremely powerful. I mean, if you follow the news on the technology advancements, you probably heard about the AlphaFold last year, where the Google DeepMind developed a graph-based algorithm to solve the protein folding problem, which was really unsolved for more than 50 years. And the second project is the deep learning-based modeling for probabilistic production forecasting in unconventional reservoirs. And again, I think for both of these areas, I mean, we have got some great results with real field examples, and you'll probably hear more about these in some of the upcoming conferences.
That's excellent. I'm excited just hearing about what you mentioned. So I'm really looking forward to those upcoming conferences and looking forward to looking more into some of the things that you mentioned. Now we'll get straight to the paper. But before I ask you details about the paper, could you walk us through what the paper is about to orient our viewers and listeners?
Yeah, sure. This paper really, I think, presents a machine learning framework for robust production forecasting in unconventional reservoirs for new wells. And it assists really operators to come up with significantly better development plans, meaning optimizing well spacing, completion design, lateral lengths, and other decision parameters. Although I mean the methodology is very generic in this paper, we applied this to an unconventional asset in Eagle Ford Basin. It was the acreage with around 250 wells, I believe. And so in this paper, I mean, we present really an end-to-end workflow, which has 4 major steps. The first step is data sculpting, which we aggregate data from different sources and systematically QC the information. The second step is feature engineering, where we use our geoscience and engineering knowledge to extract some key features from raw data that might potentially impact the well performance, such as porosity, TOC, minimum well spacing, and other parameters. The third step is training the machine learning model to forecast production, and to achieve that, we assume a functional form for production profile using the famous ARP equation. And for each phase, we build two separate machine learning models. In this case, we build models for initial production and 15 years recovery factors. And we use our explainable AutoML pipeline that we developed in-house in the company, which is also capable of quantifying uncertainty around the forecast, as we explained in the paper. And then we aggregate these the two models using a Monte Carlo approach and come up with a probabilistic production profile for each new well. And the fourth and last step is model deployment, which we run what-if scenarios, run economical analysis, and optimize decision parameters such as well spacing, completion design, depending on the objective function that the operator has. And as you see in the paper, I mean, for this Eagle Ford acreage, we built machine learning models with around 90% accuracy on the test set. And from there, we optimized the completion design, specifically amount of propellant and fluid that should be pumped into each well for the upcoming drilling campaign.
Awesome. I was really excited to read the paper, I'll be honest. And there were so many critical insights that I think the paper has that I can't wait to see like future iterations of the paper and other findings that I guess the group is going to show in the future. I just wanted to mention that.
No, thank you. Thank you.
You mentioned a little bit about the data sculpting as the initial part of the process. And I wanted to ask if you can expand on that. What's the QC process of extraction of the data using the natural language processing? Yeah.
No, absolutely. I mean, data sculpting really means aggregating all the structured and unstructured data needed in the study. Yeah? So in a systematic and semi-automated way. For data science project, I mean, as you know, we usually deal with tabular data like CSV formats, Excel, databases, etc. But in our industry, I mean, some of these key information is stored in unstructured data. For example, drilling and completion reports. And for this case study, we used the methodology that we developed in-house, which is based on computer vision and natural language processing. And we extracted a lot of key information from those completion drilling reports that the operator had. And on top of it, we extracted some very useful information on the neighbor wells from PDF reports downloaded from the Texas Railroad Commission website. One thing I have to say is a lot of this QC is done automatically and systematically by the technology that we developed, such as identifying outliers, fixing misspelling or other kind of problems that might exist in the data. But still, we went through a manual QC process to ensure data quality and actually, with most of the time in this project was spent on this manual QC. So just give you an idea, I mean, we've completed the entire work shown in this paper in 3 weeks, and that's because all the automation we have in the workflow. But around 50% of the project time was spent on data QC and aggregation. So that's typically what we spend on the data QC and aggregation before we actually start with building machine learning models.
Yes, the data QC and aggregation is definitely important. And with previous interviews I've done on the podcast, that's been a huge investment that needs to be done. And it's a very it's very important. So I'm glad that there's a large investment in time on that data QC process. Well, a little bit on that, what are some of the key data and pre-processing steps you've performed on the data?
Yeah, no, great question. I mean, we perform many data pre-processing steps before we actually train the model. But since our machine learning pipeline is automated again, I mean, it's very easy and fast to perform those. To name some of them, we check for data leakage to make sure there is no data in the feature space that is highly correlated to the target, and we don't have it on the production side once we actually want to deploy the model. We identified and treated the outliers. We did data imputation for missing values. We encoded categorical variables, and actually there are many more data pre-processing steps that we took before training the machine learning model.
Awesome. Thanks for that clarification. Now, when I've worked with developing the machine learning model and with feature selection, for instance, and I compare it to a multi-linear regression, which is a lot more basic, but some of the process in the multi-linear regression, the data exploration, and even with feature selection is looking at colinearity. So how is colinearity identified in the feature selection process and the methodology that you mentioned in the paper?
Yeah, no, I mean, that's an excellent question. I mean, you're right. I mean, we don't want to have correlated features in our model, yes? So because not only they don't really add that much information, but also they complexify the model and increase the chance of overfitting, which we're trying to avoid. So the question is, how did you identify those and remove them, correct? So we took actually 3 steps. I mean, the first step was initially before the model training, we used pairwise correlation analysis. For example, we used Pearson correlation between each one of the 2 features. And if the correlation coefficient is high, we remove one of them from the analysis. And I believe we talked about this in the paper. For example, I mean, our analysis showed early on that the temperature and depths were highly correlated. And because of that, we actually dropped the temperature from the initial feature list. The second method is dimensionality reduction. So we use principal component analysis and similar algorithms that we embedded in our AutoML pipeline. And the way we did it is we ran different scenarios during the model training to check if really dimensionality reduction had any significant impact on reducing overfitting. And the third step, which was really important, was performed after the model training. And we mainly use that for fine-tuning the model if we still had some overfitting problem. And I mean, the way it worked is like after we built the model, we ranked and quantified the impact of each one of these features on the target using the famous Shapley values, and looked for features that had negligible kind of like an overall contribution to the model. And when we found those features, we dropped them from the feature list and retrained the model to see if there was any positive impact on the overall accuracy. And the reason actually you sometimes you have that cases is you're dealing with features that are highly correlated or correlated to one or several other features, but the relationship is nonlinear and complex. Yes, and then early on, using this kind of like a simple Pearson correlation, you cannot really identify those types of correlation from the initial feature list. So those are like the three steps we took to make sure that we remove kind of like a collinearity in our modeling approach, correct, and make sure that the features are not correlated in our modeling approach.
So there was a process of identifying the collinearity before those
Correct.
features were included. Great. Just wanted to make sure if that was included in the methodology. Now, when I've worked with machine learning models as well, it's really imperative to know what's the training and then what's the validation set. That way you can know that you're predicting the model, or the model is predictive and the model is stable. So how were the training and validation sets determined? And was there a randomization that 80% is training and 20% was validation?
Yeah. I mean, yes. So we actually used stratified random sampling to split data to test on train set. Specifically, 20% was in test set and 80% in training. And the reason we use a stratified random sampling was to make sure that we have representable test sets that include low and high performing valves, as well as older and younger valves. Also, we use five-fold cross validation with shuffling to resample the training set and split them into 5 groups. 4 of them used for training each time, and 1 of them used was kind of actually the held out set for validation purposes. And that was the procedure we followed for automated hyperparameter tuning.
Awesome. Thank you for that clarification as well. I wanted to pivot to the results section of the paper because there were 2 figures in the actual versus predicted on IP and EUR. If IP has operational influences, what can be the cause of IPs being predicted so well within the uncertainty window of the 30%, but EURs having some of the outliers?
Yeah, no, I mean, that's an excellent observation. To be honest, I mean, when we first saw these results, we got a bit surprised too, but after looking more closely, there is a good, reasonable explanation for this. I mean, if you look at the feature contribution plot, I believe it's figure 11, if I'm not mistaken. The highest influencers on IP are frac parameters. And the most important factors impacting EUR are geoparameters, which makes sense actually. Yes. But one caveat with the geoparameters is we didn't have logs or cores in many of those valves, and most of these geoparameters are actually extracted from maps, which are estimates with uncertainty themselves, correct? And we believe that the uncertainties that we have in the geoparameters is one of the reasons for the EUR model not performing as well as the IP model. And also, I mean, on top of it, we had some other hypotheses. I mean, we hypothesized that maybe adding more some other features such as pressure, which we didn't have in this study, unfortunately, could potentially improve the EUR model.
Perfect. Thanks for that clarification as well. And like I mentioned, looking forward to future iterations of the paper and other parts of the analysis. For our machine learning enthusiasts, and especially when it comes to selecting for anything that's nonlinear, why was gradient boosting tree selected for the model?
Yeah, no, great question. I mean, we internally, I mean, we always kind of have the same issue. Yeah? So which model you want to choose? And I think the way we ended up doing it is in our AutoML pipeline, we embedded 11 different algorithms, so on, because everything is automated. We test all of them. So in this actually example, we use all these 11 algorithms. I mean, some of them were tree-based, such as gradient boosting tree that you mentioned, random forest, XGBoost. Some of them were kernel-based, such as KNN or SVM. And even we tried neural networks. And we also tried different stacking algorithms and came up with ensemble models that combining some of these modeling approach together. And again, I mean, we could do all this because the machine learning pipeline is automated and all these algorithms are already embedded there. And at the end, I think what we found out was the gradient boosting tree, I mean, outperformed other methods, and stacking really didn't add that much improvement to the overall performance, and that's why we decided to stick with the gradient boosting tree.
Perfect. So you did try other models, and the gradient boosting tree just ended up having the best performance.
Correct. I mean, this case, but again, some other data set you might have
another model,
random forest or other methods outperform.
So the workflow is flexible then in choosing what kind of model. Okay, that's good. That's good to hear. Not just sticking to one. Have you developed any alternative methods for unconventional production forecasting beyond what is presented in the paper?
Yes, absolutely. I mean, the workflow presented in this paper, which we call it parametric machine learning based modeling, is mainly used for capital planning purposes, for developing new acreage or infill drilling. We've also developed 2 other algorithms that have a bit of a different use case. One is automated decline curve analysis, which we automatically partition the production data into multiple segments using a proprietary event detection algorithm that we developed. And then we apply decline curve analysis to each segment. And this method is mainly used to estimate reserves on existing wells. And we've already published some articles on the topic, and if you're interested, you can refer to them for more technical details. The other one which we have developed recently, and I talked about it a bit in the beginning, is our deep learning-based modeling for multi-horizon probabilistic production forecasting. And this method is able to come up with multiple steps of forecasts for oil, water, and gas rates simultaneously. And also, I mean, we can quantify the impact of future activities such as artificial lift installation or refracs or other types of activities on the well. And it's a very powerful modeling approach. And we basically mainly use that for actively managing the producing wells, for optimizing OPEX, planning workovers, etc. And I said in the beginning, I mean, we're planning to publish more details on this method soon.
Well, I'm looking forward to that. Now, I know I've peppered you with so many questions regarding the paper, but there's one question that I'm not going to leave you away with. And that is, what are some applications of this workflow that hasn't been seen before in this industry?
Well, I mean, I think that the application is huge. Yes, I think, in my opinion, the workflow presented in this paper should be really the standard procedure for capital planning and unconventional assets. I mean, you can answer many challenging questions: how many wells you need to drill in each drilling unit, how much fluid or proppant you need to inject on each well, using a scientific, data-driven approach that is also really fast. I mean, you can come up with answers in a matter of weeks, if not days. Yeah. So, and as you know, I mean, the traditional tools such as reservoir simulation are really ineffective for decision making in unconventional. And we see many operators have been using statistical type curves for years now for decision making. But we know, I mean, those type curves are too simplistic, yes, and they cannot really capture the nonlinear and complex effect of geology, completion, well spacing, operational factors, etc., on well performance. And I think that there's a consensus out there that everyone believes that we need more sophisticated methods to make fast and data-driven decisions. And to be honest, I mean, some operators are already taking initiatives to use more powerful methods, yes, so such as machine learning in their decision making. But many are still hesitant because they think that the data science projects are costly, time consuming, and you spend all that time and money, and you might not at the end get the economics benefit that you expect, right? And the truth is, this is a valid concern. I mean, if you go about this in a conventional way and build a big team of data scientists in-house and start from scratch, and yeah, I mean, this can take months and you might not get any benefit. But the workflow actually be presenting in this paper, which is embedded in our Speedwise technology, I mean, addresses all these challenges. I mean, you're presenting a systematic and automated machine learning workflow with actual track records that can significantly reduce time and cost of those data science projects. And of course, you need to have some basic data science knowledge, but to really close the gap and have business outcome, we really recommend that engineers and geoscientists should be actually the owners of this workload, because I mean, we know, I mean, the problems we're solving in oil and gas requires domain knowledge. Yeah, I mean, if you put a data scientist without an oil and gas background, you might not actually get the effective solution you're looking for. And maybe the last one I want to emphasize is we've embedded model explanation and uncertainty quantification in the pipeline. And this is really important because it gives both the modeler and the decision maker actually the confidence before they make any decision on the asset. And this is, to me, this is a must if you really want to have any type of business impact in oil and gas. You need to be able to quantify uncertainty and try to be able to understand how your model is behaving before making any decision.
Excellent. I really like that you mentioned that we have to quantify the uncertainty before we can make that decision. I think that's really important, or before and know how the model is, or and know what are the operating ranges of that model before we can make a decision. I really appreciate that. Well, Hamed, thank you so much for letting me pepper you with questions on the podcast.
No, I mean, thank you again for having me. It was a pleasure talking to you.
Well, you heard straight from Hamed on all the information regarding SPE 200,000 and all the details based on the questions that I peppered him with. Feel free to reach out to me for any feedback on my email, and that is going to be in the description box below for the podcast. I'm Yoga Pradhan, and I'm signing out.